Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is an introduction of fluid power systems. Our objective is to introduce fluid power systems and discuss the advantages, applications, and characteristics of such systems. Additionally, we'll reacquaint ourselves with the concept of energy, power, and efficiency as applied to fluid power systems. The purpose of a fluid power system is to perform work that cannot be accomplished by an unaided human or to perform a task more efficiently with respect to time. Consider the act of some bad guy making a hero dig his own grave. The movies make it seem like excavating a 6-foot hole is an easy hour-long affair, and the only slightly dusty hero still has enough energy to do a backflip out of the grave, cut off the bad guy's head with a shovel, and sidekick his headless body into the grave. This is nonsense. Not only is the act of digging a hole a lot dirtier than movies suggest, anybody that digs a hole that big is going to be puking out of their eyes exhausted by the time they're done. Not to mention the bad guy is going to get so bored waiting for the hole to get dug, he's probably going to opt for the shallow grave option and shoot the dirty, tired hero 2 hours into the day-long process. Consider, however, a bad guy equipped with an excavator, which can move as much dirt in one scoop as an unaided human can in one day. Problem solved. Bang! World conquest is laid at your doorstep, all thanks to fluid power. Who needs superhero powers when you can uproot trees, lift trucks, and punch holes through solid steel with fluid power? A fluid power system is one in which a fluid, either a liquid or a gas, in contrast to electrical or mechanical means, is used to transmit power from one location to another. Fluid power systems come in two notable forms. Fluid power systems using liquid are called hydraulic systems, and fluid power systems using gas are called pneumatic systems. Hydraulic and pneumatic systems share some common properties. However, there are important differences between them. Both liquids and gases are states of matter differing from solids in that they take the shape of their container. Liquids, for the purposes of this lecture series, are to be considered incompressible. A certain mass of liquid occupies the same volume regardless of the available space or how much you squeeze it. Gases, however, are compressible, meaning they can contract and expand to fill containers of differing volumes. The same mass of gas can fit in a tiny capsule if compressed, as well as a large balloon if allowed to expand. Hydraulic systems most often use petroleum-based oil, whereas pneumatic systems use compressed air from the environment. This is to suggest that oil costs money, and air, for the time being, is plentiful and inexpensive. Oil, however, is a self-lubricating means of transmission and serves to minimize the friction between moving surfaces in addition to other functions. Air, in contrast, must be conditioned to do so. Both fluid mediums, in addition to transferring power, serve to lubricate and seal clearances between dynamically moving surfaces and transfer heat due to inefficiencies. Note that excessive heat can progressively damage and change the chemical nature of oil, such that the oil itself can be considered a contaminant to the system. The fluid in a fluid power system is an essential component. In later lectures, we'll discuss fluid properties and conditioning needs. Hydraulic systems are ordinarily characterized as being capable of performing medium to heavy-duty applications, whereas pneumatic systems are for light to medium-duty applications. Liquid, because of its inherent incompressible nature, means actuators, like cylinders, extend smoothly and continuously, and when in position, remain so. Gas, because of its inherent compressible nature, means actuators extend inconsistently in comparison, and when popped into position, are spongy and soft. This, in my personal opinion, is the principal advantage of hydraulic systems in comparison to all other systems, be they electrical, mechanical, or pneumatic. Hydraulic systems, in addition to being capable of lifting large loads, have incredible holding power. Liquid, being incompressible in nature, means that once pressurized flow enters a cylinder and lifts an applied load, any fluid trapped inside that cylinder may as well be replaced with a solid object if it is not allowed to leave the cylinder. Pneumatic systems must account for the compressible nature of gas. Mechanical systems must account for backlash between gears or play between mechanical linkages. Electrical systems don't really work well in static situations and often can only decelerate objects in the process of actually moving. Hydraulic systems, in contrast, are perfectly suited for such static applications. Want to lift a heavy load and keep it lifted? Let pressurized flow enter a cylinder and lift the load. Trap the liquid and forget about it. Since the trapped liquid is incompressible, that heavy load isn't going anywhere until you lower it, hopefully in a controlled fashion, by letting fluid slowly bleed out of the cylinder. We'll discuss flow control methods that allow the controlled descent of a lifted object in later lectures. Moving on. Closed hydraulic systems circulate the oil through the system, and a returning oil must be filtered, conditioned, and contained in a reservoir. Pneumatic systems, in contrast, simply exhaust the returning air to the atmosphere because, hey, why not? Air for the time being is free, and you can always get more. Finally, hydraulic systems have a deserved reputation of being dirty, greasy, oily, nasty systems. The pneumatics, in contrast, are considerably cleaner. A spill in a hydraulic system is an environmental contamination hazard, whereas a leak in a pneumatic system isn't necessarily environmentally hazardous. As if this wasn't enough, there are flammability concerns with hydraulic oil, especially around electricity and high temperatures. On a very basic level, fluid power systems are power conversion systems, where one form of input is changed to fluid power to eventually perform some task. Fluid power is characterized and controlled by pressure, flow rate, and valve position, among other properties. Ordinarily, the initial conversion to fluid power takes place in a pump, where typically rotational mechanical power, characterized by a twisting force called torque and rotational speed, is converted to fluid power. Pumps, therefore, are mechanical to fluid power converters. Ordinarily, pumps are driven by prime movers, like an electric motor or an internal combustion engine, themselves also being power converters. A motor would convert electrical power to rotational mechanical power, and an internal combustion engine would convert the stored chemical energy of old dinosaur bones to mechanical power, heat, and noise. Schematically, pumps are ordinarily represented as circles with an arrow pointing in the direction of provided pressurized flow. If the arrow is filled in, it means it's a hydraulic pump. If the arrow isn't filled in, it means it's a pneumatic air compressor. Think about it. Hydraulic systems are filled with dirty oil. The oil is black. Pneumatic systems are filled with clean air. The arrow is clear. The pump, in the case of a hydraulic system, ordinarily pumps stored oil from a tank known as a reservoir, symbolized by kind of a bathtub-looking thing. If the reservoir is vented to the atmosphere, the bathtub wouldn't have a top. If the reservoir is sealed off from the atmosphere and pressurized, the bathtub would have a top. Sometimes the fluid power schematic may include the motor and shaft linked to the pump. Electric motors are often illustrated as an M in a circle. Internal combustion engines are often illustrated as a box inside a box. Both motors and internal combustion engines can be considered prime movers. The pump isn't ordinarily directly driven by the prime mover, but rather the two shafts are linked via coupling. The coupling compensates for misalignment and allows a technician to take the pair apart for maintenance and repair purposes. When the prime mover turns the shaft of the pump produces flow measured in units of volume per time, ordinarily gallons per minute or liters per minute. The load-induced opposition to flow is what creates pressure. If the pump is just pumping into empty space, there's no pressure, and to top it off, a rapidly expanding pool of oil on the floor. While we're still kind of on the subject of pumps, let me inform you that to fully, truly, and holistically comprehend the conversion of mechanical power to fluid power necessitates an understanding of what is producing the torque and rotational speed in the first place. This is to suggest that a complete and comprehensive understanding of fluid power systems doesn't begin at the pump, but rather at the motor driving the pump. Keeping in this spirit, a complete and comprehensive understanding of motors doesn't begin at the motor, but rather at the distribution, control systems, and electrical theory behind the motor, and on and on and on into infinite chains of causality. In the interest of forward progress, however, I've got to draw a line somewhere. So I'm arbitrarily drawing a line right here. For the purposes of this lecture series, you are hereby authorized to consider everything to the left of this line, be it mechanical, electrical, or magical, as exactly that. PFM. Pure magic. Later lectures will revisit these crucial points of interaction in greater detail. Expect me at some point in the future to level with you and admit all our previous assumptions are in fact cartoonish simplifications. I can't blame you for being mad at me for withholding information, but realize I'm withholding a lot of information for you for two important reasons. One, it's not important now. And two, I operate under the Kung Fu principle, and that I am always entitled to withhold one trick from you lest you come back at a later date and challenge me. I, quite like your mama, continually reserve the right to set you on my knee and spank you, regardless of your age or profession. Moving on. As previously mentioned, fluid power is characterized by several properties, notably pressure, flow rate, and valve position. A fluid power system is only effective if these properties are controlled and measured. As we'll later learn, there exists a degree of crosstalk between these properties, but for now, we can make this bold and memorable simplification. Pressure is strength, flow rate is speed, and valve position is direction. If you can walk away from this entire lecture series with just this simple understanding, I will consider my time having not been spent in vain. The principle that largely governs fluid power systems is known as Pascal's Law, which in summation states that when force is applied to a confined fluid in a closed system, it exerts pressure equally in all directions. A large number of introductory fluid power principles can be demonstrated using a pair of syringes linked by a hose. When two empty syringes are capped off, there is a quantity of air entrapped between the two pistons. This entrapped air is now a confined fluid, and this is a basic pneumatic system. As I push in one of the syringes, the entrapped air pushes on the face of the other piston, and the other syringe extends. Air is being employed as a means of power transmission, in contrast to mechanical or electrical means. The pistons needn't be in line with one another, and could be angularly offset from each other as an example. As long as they're linked by a passageway, gas can be used to transfer power in this simple pneumatic system. Note the inconsistency with which the pneumatic actuators extend. There's a bit of lag in actuation. Additionally, note the sponginess of an actuator supporting a load. These observed characteristics are due to the compressible nature of air and something that must be accounted for in a pneumatic system. In contrast, when the two syringes are filled with water and capped off, the entrapped water is now a confined fluid, and this is a basic hydraulic system. As previously, I can push in one syringe, and the piston face pushes on the entrapped water, and the entrapped water pushes on the face of the other piston, and the other syringe extends. Liquid is being employed as a means of power transmission in contrast to gas, mechanical, or electrical means. As previously, the pistons needn't be in line with one another and could be angularly offset from one another. As long as the two cylinders remain linked by a passageway, liquid can be used to transfer power in this simple hydraulic system. In contrast to our previously examined simple pneumatic system, note the consistency, predictability, and regularity with which the hydraulically driven actuators extend. There's no lag in actuation. Additionally, note the firmness of a hydraulic actuator supporting a load. These observed characteristics are due to the incompressible nature of liquid and present a major advantage over pneumatic systems. In the interest of fairness, when a pneumatic system springs a leak, it's far easier to clean up than a leak in a hydraulic system. Note the simple fluid power system examples use cylinder actuators relatively similar in size. Consider, however, two different size cylinders forming a force multiplication system, one of the principal applications of fluid power that trades distance for force. When force is exerted on the smaller piston, pressure is exerted on the confined fluid. The confined fluid through the passageway exerts pressure on the larger piston, and it extends with a larger force. However, due to the area differential between the cylinders, the volume displaced in the smaller cylinder only extends the larger cylinder a small distance. In a perfectly lossless system, energy input equals energy output. A small force applied over a long distance equates to a large force applied over a short distance. If you want to think of it this way, a force multiplication system is the fluid power equivalent of a step-down gearbox that trades speed for torque. We'll examine Pascal's Law and force multiplication systems in greater detail in later lectures. But for the purposes of this lecture, let's quickly define force as a measurable push or pull in units of pounds force or newtons. Pressure, in contrast, is force per unit area, as in pounds force per square inch, often abbreviated PSI, or pascals, where 1 pascal is a newton of force applied over a square meter. Area is ordinarily expressed in units of square inches or square centimeters. The units tell the story quite nicely. Force equals pressure times area. Pound force per square inch times square inch yields pound force. This is Pascal's law. If a comparatively small pressure acts on a large area, force increases. Think about a sailboat on a light wind day. If you want to go somewhere, you need a big sail. In contrast, on one of those nuking days when fish are being blown out of the water, you might need to trim the sails to stay in control or reduce force. Simply by modifying pressure and functional area, one can control the applied force. Going back to our earlier diagram, this implies that the end result of a fluid power system is ordinarily the eventual conversion of fluid power into mechanical power. Actuators are the business end of a fluid power system where this conversion takes place. Linear fluid power actuators are known as cylinders. Cylinders extend and retract with a definable force, speed, and direction as dictated by the fluid power system pressure, flow rate, and valve position. Cylinders are ordinarily represented schematically as one would see them if bestowed X-ray vision and examined in profile. Pending construction variants, the schematic symbol may be modified accordingly. Rotational fluid power actuators are known as hydraulic motors. Motors turn clockwise or counterclockwise with a torque and rotational speed, as dictated by the fluid power system pressure, flow rate, and valve position. You'll note the hydraulic motor schematic symbol is essentially the opposite of a pump. It's an actuator that converts fluid power to rotational mechanical power. Its schematic symbol has arrows pointing into it, meaning it is consuming fluid power and converting it to rotational mechanical power. Note if the hydraulic motor is bidirectional, i.e. you can spin two opposite directions, it'll have two arrows pointing in opposite directions. Again, the arrows indicate that the hydraulic motor is consuming fluid power to our system, whereas the arrows in a pump indicate the pump is providing fluid power to our system. Both these actuators, cylinders and motors, can be used to lift, lower, push, pull, tip, tilt, turn, crush, pound, or otherwise manipulate a load. Keep in mind, mechanical linkages can modify the initiating motion. A linearly actuating hydraulic cylinder can turn or tip a load using a pivoting mount. If you step back a bit, you can think of a fluid power system just like every other system you've ever looked at. There's a power source, a means of transmitting the power, and a load being manipulated. Some of you might be like, wait a minute, hold everything. You mean to tell me that a motor converts electrical power into rotational mechanical power? A pump converts rotational mechanical power into fluid power, The fluid power system controls and measures pressure, flow, and valve position just so some dumb hydraulic motor can convert fluid power back into rotational mechanical power? Why didn't you just use an electric motor in the first place? Can't an electric motor just convert electrical power straight into rotational mechanical power without all the hoo-ha and hand-waving and dirty, greasy, noisy hydraulics? My question exactly. There are advantages and disadvantages to be considered every time energy changes form, and complexity, cost, and efficiency are at the forefront of these considerations. Systems need more complexity, like Portland, Oregon needs another Thai food cart. With each energy transition, losses occur and troubleshooting opportunities magnify. Losses in fluid power systems include, but are not limited to, heat, unintended pressure drops, friction, noise, leaks, and resistance in hoses, piping, and fittings due to kinks, twists, and bends. We'll discuss efficiency in a moment. However, complexity and accounting for inefficiencies can be an acceptable trade-off if one form of power transmission presents notable advantages over others. When it comes to rotational actuators, the electric motor is my weapon of choice. I am not going to build a high-range electric car driven by a hydraulic motor. This being said, an excavator with a fluid power system driven by an internal combustion engine can power rotational actuators and a harvester attachment to cut, limb, and manipulate a huge tree without the necessity of powering an electric motor. I'm equally a huge fan of hydraulic cylinders when it comes to linear actuators. I'm not going to lift a bridge with an electrical solenoid, a comparatively weak linear electrical actuator best suited for small-scale movements with very limited holding ability. This being said, I am going to use an electrical solenoid instead of a huge high-pressure hydraulic cylinder to close a tiny electrical switch in a relay. These examples suggest that there are applications and scales befitting one form of power transmission over the other. Fluid power systems, particularly hydraulic systems, are known for their ability to manipulate or lift large loads and keep them lifted with no additional expenditure of energy. Fluid power systems, in contrast to electrical systems, are also known to have lower initial cost. This does, however, come at a price. Fluid power systems are notoriously noisy, they have cleanliness and environmental concerns, and making up for the lower initial investment cost, require routine maintenance that, if neglected, can lead to systemic failure. The progressive decay of oil exposed to excess heat is a classic example. Additionally, fluid power systems come with unique safety concerns, principally the ever-present possibility of catastrophic ruptures and pinhole leaks associated with high pressures, the slip, trip, and fall hazards presented by spilled hydraulic oil, and the very real possibility of having valuable portions of your anatomy crushed to a pulpy goo between an irresistibly moving hydraulic actuator and an immovable object. Hybrids of different systems exist for the purposes of mitigating disadvantages and maximizing advantages. Consider an electrically controlled hydraulic system where a high-pressure hydraulic cylinder is controlled by a precise and responsive electrical control system. Astounding speed and accuracy can be achieved, all without sacrificing the immense lifting and holding capability of hydraulics. As I like to think of electrically controlled hydraulic systems, hydraulics are the muscle, and electrical control is the brain. Let those forms and methods that excel in one particular function perform that function to the exclusion of all others. Ultimately, regardless of the flavor, the different aspects of a larger system work together toward the fulfillment of a goal. Returning to our previous discussion on fluid power properties, let's briefly discuss how these properties are controlled and measured by a fluid power system to perform a task. Pressure, the property that influences the actuation strength of a fluid power system, is largely governed by pressure control valves. Pressure control valves include, but are not limited to, pressure relief valves, sequence valves, counterbalance valves, pressure reducing valves, and unloading valves. Don't bother differentiating between these very similar looking schematic symbols right now, because we'll revisit each of these pressure control valves in a later lecture. Each pressure control valve performs a specific function that ultimately influences the strength of the fluid power system. Pressure is measured using a pressure gauge or manometer, symbolized by almost a clock-looking dial with a needle that points at the pressure reading. Pressure switches and pressure sensors, sometimes called pressure transducers, perform automatic monitoring of pressure for electrically controlled fluid power systems. We'll examine these measurement devices in greater detail in later lectures. Flow rate, the property that influences the actuation speed of a fluid power actuator, is governed largely by the pump and prime mover combination. If a pump has a certain volumetric displacement per revolution, the prime mover can vary rotational speed up or down to change flow rate. Similarly, if the prime mover remains at a fixed constant speed, a variable displacement pump can vary the displacement per revolution to change resultant flow rate. Flow control valves can then be used to throttle flow rate down from there. Flow control valves ordinarily feature a restricted orifice that can be varied opened or closed as conditions dictate. Flow rate is measured using a flow meter, symbolized by a baseball-looking thing. Flow meters are ordinarily direction and gravity dependent, meaning that flow to be measured must come in the indoor and out the outdoor if the flow meter is to return accurate data. Additionally, some flow meters must be vertically mounted such that the flow rate goes upwards through them. A flow meter intended to be mounted vertically, in to out, bottom to top, won't read accurately if it's mounted on its side, upside down, or if the flow is routed through it backwards. A needle slides up and down on a scale, indicating flow rate in the desired unit. Additionally, flow switches and flow sensors also exist to automatically monitor flow rate for electrically controlled fluid power systems. Finally, valve position, the property that influences actuation direction of a fluid power actuator, is governed largely by check valves and directional control valves. Check valves are one-way valves that allow fluid flow in one direction but disallow it in another. The schematic symbol for a check valve looks like a ball in a seat because that's exactly what it is. In the block position, the ball is forced onto the seat and no fluid can flow. In the flow direction, the ball is forced off the seat and fluid can flow. Directional control valves are valves that can be shifted from position to position where pressurized flow, P, is routed to one actuator port, either A or B, and the opposite port is routed to tank, T, or in the case of a pneumatic system, E, for exhaust. The schematic symbol for a directional control valve includes a means of positioning the valve for a deactivated position, ordinarily a spring, a means of actuating the valve, either manually or electrically with a solenoid, a finite number of positions the valve can be placed in, and a number of passageways that can be connected or disconnected based on the position. As a preview of how a directional control valve operates, consider this three-position, spring-centered, manually actuated directional control valve with a closed center, a straight-through position, and a cross-connect position. When the valve is in the spring-centered, closed position, the hydraulic cylinder neither extends nor retracts. Given liquid is an incompressible medium, this position could be used to quasi-indefinitely hold a load in position. If an operator manually shifted the directional control valve to the straight-through position, pressurized flow is routed to the A port, and the B port is dumped to tank. In this application, the cylinder would extend. If an operator manually shifted the directional control valve to the cross-connect position, pressurized flow would be routed to the B port, and the A port is dumped to tank. In this application, the cylinder would retract. In addition to operators manually monitoring and operating fluid power systems, consider electrically controlled fluid power systems that automatically monitor position with the use of mechanical limit switches, magnetic proximity switches, and position transducers that output a voltage or current signal proportional to position. Automated systems do not necessitate constant human supervision. Later lectures will examine fluid power schematics, directional control valves, flow control valves, pressure control valves, and much more in greater detail. I'm just trying to give you a big picture up front and give you an idea of where we're eventually headed. It might seem like you're drinking from a fire hose right now, but trust me, it'll all make sense in time. Before we close up shop, let's do a quick review of energy, power, and efficiency as applied to fluid power systems. I'd be remiss in my duties as an instructor if this lecture didn't include any tedious illustrated example problems. Consider this a light warm-up for later exercises, because I hate for you to pull a muscle just when we're starting to have fun. Recall from the Energy and Power lecture from way back in the Basic Electronics 1 DC Circuit Analysis playlist that energy, among its many forms, can be considered as a force expressed for a distance. Linear exertions of energy should be easy. Take a force in units of pounds, force, or newtons and multiply it times distance, either feet or meters. The result is energy, either in units of foot-pounds force or joules, where joule is 1 newton of force expressed for a distance of 1 meter. Consider a hydraulic system tasked with lifting Cuban American rap star Pitbull on stage way back in 2004. Mr. Worldwide at that time weighed about 180 pounds. And let's say the system had to lift him a height of 6 feet. If energy is force times distance, this means the system exerted 180 pounds force times 6 feet, or 1,080 foot-pounds force of energy. Which brings us to the present day. After a couple years living La Vida Walmart, let's say Pitbull now represents a 230-pound load and still needs to be lifted a height of 6 feet. If energy is again force times distance, the hydraulic system now needs to exert 230 pounds force times 6 feet, or 1,380 foot-pounds force of energy. A larger force expressed over the same distance required more energy. It makes sense. Power, in contrast, is the time rate consumption or production of energy. Power is energy over time. A visual representation of this three-variable relationship using a triangle is extremely useful. Let's say the hydraulic system in 2004 needed to get the 180-pound Pitbull to the stage 6 feet away in a matter of 2 seconds. Power is energy over time. 1,080 foot-pounds force over 2 seconds yields a power input of 540 foot-pounds force per second. A common power unit, the horsepower, happens to be 550 foot-pounds force per second, and a simple unit conversion shows us that this task requires, at minimum, just shy of 1 horsepower to accomplish it in the time desired. Consider this same sub-1 horsepower system, limited to producing 540 foot-pounds force per second, being used to lift Mr. Worldwider on stage in the present day. How long would it take this system to lift a 230-pound load a distance of 6 feet? If power is energy over time, a simple algebraic rearrangement suggests that time is energy over power. Substituting in our given values, we find this system would take approximately 2.6 seconds to accomplish this same task. It makes sense. A larger force expressed over the same distance took slightly longer to do so when our output was limited to a fixed value. What if, however, we really did need to lift him on stage in exactly 2 seconds in the present day? What is the power requirement for this task? Again, power is energy over time. 1,380 foot-pounds force over 2 seconds yields a necessary power input of at least 690 foot-pounds force per second. It makes sense. A larger force expressed the same distance over the same time span necessitated a more powerful system to do so. Converting this value to horsepower yields a value of approximately 1.3 horsepower. If you want to, you could convert this to 935.9 watts, because 1 horsepower equals 550 foot-pounds force per second, and 1 horsepower also equals 746 watts. As I explained in the unit conversion lecture, the horsepower, despite its antiquated and somewhat inaccurate measurement of a true horse's power, it's actually quite a handy means of converting between these two commonly used unit systems. If you're tracking, you should be able to knock out the following example problems with no delay. Consider a lift system in a garage that must lift a 5,630-pound pickup truck a height of 5 feet to perform some maintenance. How much energy must be put into this system? By all means, pause the lecture and take your best shot at this. Energy equals force times distance. 5,630 pounds force expressed at a distance of 5 feet yields 28,150 foot-pounds force of energy. Let's say it took this lift an agonizing 12 seconds to accomplish this task. How powerful is this system? Power is energy over time. 28,150 foot-pounds force over 12 seconds yields a power input of approximately 2,345.8 foot-pounds force per second. If we wanted to convert this to horsepower or watts, a simple unit conversion shows us that this necessitates approximately a 4.3 horsepower system, or equivalently, a 3.2 kilowatt system. What if the garage wanted to upgrade, repair, or replace the lift such that it could accomplish the same task in a matter of only 8 seconds? Again, power is energy over time. The task has not changed. A 5,630 pound object must still be lifted a height of 5 feet. The only demand is that it now be done quicker. This will obviously necessitate a more powerful system. 28,150 foot-pounds force over 8 seconds yields approximately 3,518.8 foot-pounds force per second. If we wanted to convert this to horsepower or watts, a simple unit conversion shows us that this necessitates approximately 6.4 horsepower, or equivalently a 4.8 kilowatt system. Note those illustrated example problems neglected any complexity and inefficiencies we previously discussed. Consider the following simplification of the cascaded nature of power conversion. A motor converts electrical power to rotational mechanical power. The pump converts rotational mechanical power to fluid power, and the cylinder actuator converts fluid power to linear mechanical power. Each conversion process can be modeled as a stage, which receives input and produces output, of which a portion is considered a loss due to inefficiencies. Consider our first scenario, in which the lift took an agonizing 12 seconds to lift the 5,630 pound truck 5 feet. This system yielded a power output of 2,345.8 foot-pounds force per second. Let's say the cylinder actuator and fluid power system is 86% efficient at converting fluid power to linear mechanical power, accounting for any leakage, friction, heat loss, restriction in pipes, fittings, or bends, and any unintended pressure drops across valves. Let's say the pump is only 60% efficient at converting rotational mechanical power to fluid power, accounting for any leakage, play in the coupling, and friction. Let's say the motor is 88% efficient at converting electrical power to rotational mechanical power, accounting for heat losses in the windings and friction. This cascaded system, accounting for inefficiency, must therefore have far more power input to it if it is to yield the necessary 2,345.8 foot-pounds force per second power output. Recall that efficiency, like most three-variable relationships, can be visualized with the use of a triangle. Efficiency is a ratio, typically expressed as a percentage of output over input. We know our desired output, and we know the efficiency of each stage. It is a trivial algebraic manipulation to solve for input, where power input equals output over efficiency. Substituting in our observed quantities, we find that the fluid power system converts only 2,345.8 foot-pounds force per second of the available 2,727.7 foot-pounds force per second to usable linear mechanical power, 14% of which is considered a loss to the system. Similarly, we find that the pump converts only 2,727.7 foot-pounds force per second of the available 4,546.2 foot-pounds force per second of rotational mechanical power to usable fluid power. The remaining 40% of this input is considered a loss to the system. Finally, we find that the motor has converted only 4,546.2 foot-pounds force per second of the available 5,166.1 foot-pounds force per second of electrical power to usable rotational mechanical power. The remaining 12% of this input is considered a loss to the system. All in all, this system needs to consume 5,166.1 foot-pounds force per second of electrical power. Or to put this in a unit more commonplace for electrical calculations, approximately 7 kilowatts of electrical power to produce the requisite 2,345.8 foot-pounds force per second, or approximately 3.2 kilowatts of linear mechanical power. This is to suggest that the whole system is 88% times 60% times 86%, or only approximately 45% efficient. Given the pump is the weak link in our system, consider not an expensive upgrade of this system, but rather a troubleshooting and maintenance procedure that identifies and corrects a misalignment or a damaged coupling between the motor and pump shaft, such that this stage now converts 80% of the rotational mechanical power to fluid power. Let's work through this example problem the opposite direction, from input to output, operating under the assumption that the motor still consumes approximately 7 kilowatts of electrical power. Due to inefficiencies, only 4,546.2 foot-pounds force per second is converted to rotational mechanical power. An algebraic rearrangement of our efficiency relationship suggests that power output is equal to efficiency times input. Substituting in our given efficiency and input values, it shows that the repaired pump stage now outputs approximately 3,637 foot-pounds force per second of fluid power. The 86% efficient fluid power system and cylinder actuator in turn converts this to 3,127.8 foot-pounds force per second of linear mechanical power. Given that the original task took 28,150 foot-pounds force of energy, and the fact that time is energy over power, it can be shown that this repaired system takes only 9 seconds to accomplish the same task. It makes sense. A cascaded system with a more efficient stage yielded quicker results given the same input conditions. Alright, this about wraps up our brief introduction of fluid power systems. Again, this lecture might be introductory in nature, but it covered a lot of important material in a short period of time. I'm encouraging you to rewind, review, and revisit this lecture as needed. In conclusion, this lecture took a brief look at fluid power systems. We defined fluid power systems and identified critical fluid power properties, pressure, flow rate, and valve position, and discussed how these properties must be controlled and measured by a fluid power system to control the strength, speed, and direction of the resultant mechanical output. We introduced a couple basic fluid power devices, discussed their general purpose, and drew their associated schematics. We differentiated between hydraulic and pneumatic systems, compared and contrasted the characteristics, advantages, and disadvantages of fluid power systems with other systems, and finally, we reacquainted ourselves with the concept of energy, power, and efficiency as applied to fluid power systems. Remember to review these concepts as often as you really need to drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.